In 1981, Stephen Hawking stood up at a conference and said something that made my blood run cold. He said information that falls into a black hole is destroyed, gone forever. Now, you might think that's just an interesting claim about black holes. But what Stephen was really saying, whether he knew it or not, was that quantum mechanics is wrong. The entire foundation of modern physics was wrong. And I couldn't let that stand. For 28 years, Stephen and I went to war over this. Let me tell you why I had no choice. It was 1981. I was at a workshop in San Francisco, one of those small, intense physics gatherings where everyone sits around arguing about the latest ideas. Stephen Hawking was there. Now, Stephen had made his name in the 1970s by proving that black holes radiate. They're not perfectly black. They give off this faint glow of particles, now called Hawking radiation. Brilliant work, revolutionary. I had enormous respect for the guy, but at this workshop, Stephen took his argument one step further. He said that when a black hole evaporates completely, when all that Hawking radiation has leaked out and the black hole is gone, the information about what fell in is destroyed. Permanently. You drop a book into a black hole, the black hole evaporates, and the information in that book is just gone. Erased from the universe. I remember sitting there, listening to him explain this, and thinking, that can't be right. See, there's this principle in quantum mechanics, maybe THE most fundamental principle, called unitarity. It says that information is never destroyed. Ever. The universe might scramble information, hide it, make it incredibly difficult to decode, but it never actually destroys it. This isn't some optional feature of quantum mechanics. This is the core. If you break unitarity, you break quantum mechanics. The whole thing falls apart. And here was Stephen Hawking, one of the greatest physicists of the 20th century, calmly telling us that black holes break this rule. That quantum mechanics, when pushed to its limits, just gives up. I went up to him after the talk. I said, Stephen, you can't be serious about this. You're saying quantum mechanics is wrong. He looked at me with that slight smile of his and said, yes, Leonard, I think quantum mechanics will have to be modified, like it was a minor software update. I walked out of that room furious. Not at Stephen personally. He was following the logic of his calculation, and you have to respect that. But furious at the idea. Because if Stephen was right, if information could be destroyed, then everything I'd spent my career studying, quantum field theory, particle physics, the whole quantum framework, was built on sand. That's when I realized this isn't just a disagreement about black holes. This is a fight for the soul of physics. And I had to fight it. All right? Let me explain the problem the way I see it. And I'm going to use an analogy that actually works. Imagine you've got a book, any book. Let's say it's the complete works of Shakespeare. Now you throw that book into a fireplace. The book burns. The pages turn to ash. The ink molecules break apart. The whole thing gets scrambled into smoke and heat and little bits of carbon. Now, here's the question, is the information in that book destroyed? Your first instinct might be to say yes. The book is gone. Shakespeare's words are gone. But here's the thing. According to the laws of physics, the answer is no. The information is still there. It's scrambled, sure. It's spread out among trillions of smoke particles and photons and heat radiation. But in principle, IMPR and CIPLE, if you could track every single particle that came out of that fire, every photon, every ash molecule, you could reconstruct the book. You could reverse the process. The information is preserved. This is what physicists mean by unitarity. The laws of physics are reversible. You can run the movie backward. Information is never created or destroyed, it's just reshuffled. Now, Stephen Hawking comes along and says black holes are different. When you drop that book into a black hole, the information really is destroyed. You can't get it back, not even in principle. The laws of physics at the event horizon are fundamentally different from the laws everywhere else. And look, I understood why he thought this. His calculation was elegant. Here's how it goes when something falls into a black hole. It crosses the event horizon. That's the point of no return. Once you're past that boundary, you can't get back out. Not even light can escape. So the information seems trapped inside. But then Hawking showed that black holes radiate. They give off particles. And these particles, according to his calculation, are completely random, thermal radiation. Like the heat coming off a hot stove. No information in them whatsoever. Just random quantum noise. So you drop Shakespeare into a black hole. The black hole slowly evaporates through Hawking radiation. Eventually, the black hole is gone completely, and all you're left with is this random thermal glow. The information about Shakespeare is nowhere to be found. That's the problem. That's what Stephen claimed. Now, most physicists heard this and thought, wow, interesting. Black holes must be special. They were willing to accept that maybe quantum mechanics doesn't apply near black holes. Maybe Einstein's general relativity wins out and information really can be destroyed. But I couldn't accept that. Because here's what people weren't seeing: if black holes can destroy information, then NYTG can destroy information. You just have to make a black hole, collapse some matter, wait for it to evaporate, boom, you've destroyed information. And if you can do it once, you can do it anywhere. The whole structure of quantum mechanics falls apart. So I had two choices. Either accept that quantum mechanics is wrong, that the most successful theory in the history of physics needs to be thrown out and rebuilt from scratch, or prove that Stephen's calculation was missing something, that the information isn't actually destroyed, that it gets out somehow. I chose to fight. For the first 10 years, from 1981 to about 1991, I didn't have a solution. I just had a conviction. I knew Stephen had to be wrong, but I couldn't prove it. I'd lie awake at night thinking about this. How does information get out of a black hole? Where does it go? Then in 1993, I had a conversation with Gerard Hooft that changed everything. Gerard is one of the smartest physicists I know. Dutch guy, Nobel Prize winner, brilliant mind. He'd been thinking about black holes too, and he had this radical idea. He said, what if all the information about what falls into a black hole is actually stored on the surface, on the event horizon itself, not inside, on the boundary? I remember hearing this and thinking, that's crazy. How can information be in two places at once? If you fall into a black hole, you're inside. Your information is inside. But the outside observer sees you smeared on the horizon, burned up by radiation. Both can't be true. And then I realized maybe they can both be true, just not to the same observer. That's when I came up with black hole complementarity. Here's the idea. Let me use an analogy. Imagine you're watching a friend fall into a black hole. From your perspective, outside the black hole, you see your friend hit the event horizon and then appear to freeze. They get stretched and redshifted and eventually fade away into the Hawking radiation. To you, it looks like your friend was burned up on the horizon. Their information is encoded in the radiation that comes out. Nothing went inside. But now imagine you're the one falling in. From your perspective, you sail right through the event horizon. Nothing special happens. No firewall, no barrier. You just keep falling toward the singularity at the center. From your point of view, your information definitely went inside. So which is true? Did you get burned up on the horizon, or did you fall through? The answer is both. It depends on the observer. And this is the key point. No single observer can ever see both descriptions at the same time. If you're outside, you see the horizon version. If you're inside, you see the falling version. But you can't be both outside and inside simultaneously. So you never see a contradiction. It's like quantum mechanics itself. An electron can be in two places at once until you measure it. Then it's in one place. Black hole complementarity says the same thing. The information can be in two places at once, inside the black hole and on the horizon. But any single observer only sees one version. I called this black hole complementarity. I wrote it up with two colleagues, Russ Thorlacius and John Uglum, and we published it in 1993. The paper was called The Stretched Horizon and Black Hole Complementarity. I was so excited when we submitted it. I thought, this is it. This solves the information paradox. Stephen has to accept this. Stephen did not accept this. He came back and said, Leonard, you're just avoiding the problem. You're saying information is both inside and outside, but you're not explaining how it gets out. You're not explaining the mechanism. And he had a point. Complementarity told us that information must be preserved, but it didn't tell us where it goes or how we could recover it. It was a principle, not a mechanism. So I kept working. The next big step came in 1994 when I wrote The World as a Hologram. This was me building on Gerard Hooft's idea and taking it to its logical conclusion. I proved that the information content of any region of space is not proportional to its volume, it's proportional to its surface area, like a hologram, a 3D image encoded on a 2D surface. For a black hole, this means all the information inside is encoded on the horizon. The horizon is the hologram, the interior is the image. This was huge. This gave us a way to think about where the information goes. It's on the surface. It's been there all along, but Stephen still wasn't convinced. He kept pushing back. Where's the mechanism? He kept asking, how does it get out? And honestly, for a long time, I didn't have a complete answer. I just knew it had to be true. The physics community was split right down the middle. It was like watching a boxing match. Team Hawking versus Team Susskind. On Stephen's side, he had the calculation, he had the math. His equations clearly showed that Hawking radiation is thermal and random. If you insisted information comes out, you explain H or bow, and nobody could do that. On my side, I had unitarity. I had quantum mechanics. I had the holographic principle. I was saying, look, the calculation must be missing something. Maybe the Hawking radiation isn't perfectly thermal. Maybe there are subtle correlations that encode the information. The debates got intense. I remember a conference in Santa Barbara in 1997 where Stephen and I went head to head in front of a room full of physicists. He presented his arguments. I presented mine. People were taking sides. It was exhilarating and exhausting at the same time. But here's the thing. Even though we disagreed, even though we were fighting over this for decades, I had enormous respect for Stephen. He was following the logic of his calculation. He was being a scientist, and he was pushing me to be better, to find the actual mechanism, not just the principle. Then, in 1997, Juan Maldacena published his ATTIS CFT paper. This was a game changer. Juan showed that there's a precise mathematical relationship between quantum gravity and anti-de Sitter space and a quantum field theory on the boundary. It was a concrete realization of holography. And in this setup, information is de fait preserved. There was no ambiguity. After Maldacena's work, the tide started to turn. More and more physicists started accepting that information must be preserved. The question shifted from, is it preserved, to how exactly does it get out? And then in 2004, Stephen conceded. We were at a conference in Dublin, the GR17 Conference on General Relativity. Stephen gave a talk where he announced that he'd changed his mind. He said he now believed information is preserved in black holes. He'd lost the bet. Now, some people said he conceded too early, that the mechanism still wasn't fully understood. And they're right, we still don't have all the details. But the principle is clear. Quantum mechanics wins. Information is preserved. I felt vindicated, of course. But I also felt something else, relief. Because if Stephen had been right, I would have had to rethink everything I knew about physics. And honestly, at this point in my life, I didn't want to start over. So that's the story of the black hole war. But it's not the end of the story. Because even though we know information is preserved, we still don't fully understand the mechanism. In 2012, a group of physicists, Almeri Marolf, Polchinski, and Sully came out with the firewall paradox. They said if information comes out in Hawking radiation, then the event horizon must be a violent firewall that incinerates anything that crosses it. This seemed to contradict everything I'd said about complementarity. I spent months thinking about this, and then I had another breakthrough. Juan Maldacena and I came up with the ER-EPR conjecture in 2013. The idea is that quantum entanglement, the spooky connection between particles, is actually a wormhole. In Einstein-Rosen bridge, ER equals EPR, entanglement creates geometry. This solved the firewall problem, or at least it gave us a new way to think about it. The information doesn't have to violently escape the horizon. It's already connected to the outside through quantum entanglement, through wormholes. My current work is all about this. I'm 86 years old now, and I'm still working on black holes. My students and I are studying quantum complexity, how fast black holes scramble information, how computational complexity grows inside black holes, how all of this connects to the structure of space-time. We've even simulated wormhole-like behavior on a quantum computer. My colleague Adam Brown and I published a paper in Nature in 2022 showing this. We're getting closer to understanding the mechanism. But I'll be honest with you, I don't know if we'll have the complete answer in my lifetime. This problem has consumed 45 years of my career. I've gone from a young physicist fighting Stephen Hawking to an old man still chasing the same question. And I love it. This is what physics is. You find a problem that seems impossible, you fight it for decades, and slowly, you chip away at it, you get closer to the truth. So why did quantum mechanics force me to fight Hawking? Because I had no choice. If Stephen had been right, it would have meant that the most fundamental law in physics, the preservation of information, was wrong. It would have meant throwing out quantum mechanics and starting over. And I couldn't accept that, not without a fight. Some people ask me, was it worth it, spending 28 years on one problem, fighting with one of the greatest physicists of all time? Absolutely. Because this isn't just about black holes. It's about the nature of reality itself. It's about whether the universe is fundamentally quantum or whether there are exceptions. It's about whether information is sacred or whether it can be destroyed. And after all these years, after all the arguments and papers and late nights, I believe this: the universe is quantum. Information is preserved. The laws of physics don't have exceptions. Black holes are the most extreme objects in the cosmos, the densest, the most gravitationally intense, the most mysterious. If quantum mechanics survives black holes, it survives everything. That's what I fought for. That's why I couldn't back down. And you know what? After 50 years of doing physics, the universe still surprises me. I still wake up excited to work on these problems. I'm still learning, and that's the real victory. The black hole war is over. But the quest to understand quantum gravity, to unite quantum mechanics and general relativity into one coherent picture, that war is still going on, and I'm still in the fight.